In this video, I want to consider the movement of sediment on sandy beaches. But let's start by just thinking about just the overall sand budget of beaches. So where does the sand come from? Well, there are basically two sources. One is rivers. Rivers carry sediment. When they reach the coast, they deposit that sediment into the sea, and that sediment gets washed down the sea by waves. You can see in this picture that kind of milky water here. That is all milky because it contains sediment. The second source of sediment is the land itself. When the land consists of unconsolidated sediment, or in this case sand, this is a typical Florida beach, as waves erode away the land, they are creating or adding sediment to the beach system from the land. So all this material here, which at one point was part of the land, is now going to become part of the beach. So that's where the sand comes from, but where does it go? Well, ultimately, there are certain places where sand is completely and permanently lost from the beach system, and they tend to be places that put the sand out of the reach of normal waves. And a good example would be a deep submarine canyon, as you might see along an active margin along, say, the Pacific coast, where the sand, if it falls into this canyon, it gets dropped way down here onto the abyssal plain, and once it's down there, there's no way it's coming back up to contribute to the beach. So in general, permanent loss of sand involves taking the sand away from the shoreline and moving it far enough offshore where it can't return. A really good example of a sediment budget type analysis that leads to an explanation for erosion comes from Southern California, just north of the town of Ventura, California. Here it is over here on the Southern California coast. So the sediment at Ventura is delivered to the area from the Ventura River, which drains this huge watershed in green. And so the watershed drains water and sediment, and that delivers sediment to the coastline here. And there was a balance between the material, the sediment added by the river, and the sediment removed by natural wave erosion processes, which maintain the beaches just west of Ventura. However, in some point in the 1980s, I believe, a dam was erected up on Matalicha Creek up here in the northern part of the watershed. This dam, Matalicha Dam, there it is there, intercepted the water and also intercepted sediment. So in back of the dam here, not only is there water accumulating, but all the sediment that would be flowing out and through the Ventura River and out onto the beach in Ventura is now trapped or impounded behind that dam. And that reduction in the input of sand to the beach system here in Ventura resulted in massive erosion. So this is what the beach looked like at Ventura Beach following the construction of the dam. So now the equilibrium has been upset. So now less material is being added as being removed, and with that change, the beach has undergone rapid erosion, and you can see in this case that the erosion has actually eaten into the structures of the roads and stuff like that. And all of this happened because the input supply of sand was interrupted. Now we're going to focus not on those kind of processes in this class, but on processes that are more appropriate for a typical depositional coastline, passive margin coastline like we have in Florida. So what I want to focus on next are the processes that actually move sediment or sand mostly around on these typical sediment-rich beaches that we have in our backyard. We can distinguish two different types of processes. The ones that move sand largely parallel to the shore, indicated by the blue arrow here, and the processes that move sand perpendicular to the shore, indicated by the red arrows. Now, the sediment moved parallel to the shore dominantly occurs by a process called longshore drift. And longshore drift is something that happens right in the swash zone, the place where waves crash and that frothy water spills onto the beach and then returns under the pull of gravity back to the sea. So as that happens, here's a little cartoon happening here. If waves and winds are arriving on the beach at an angle, not perpendicular to the beach, but at an angle, the swash, the movement of that frothy water up the beach, will be at an angle like this. So the water is pushed up the beach at an angle, the momentum of the wave pushes it up the beach at an angle, it loses its steam, and then gravity takes it and returns that water right back down right back down perpendicular to the beach. And then the next big wave takes it and moves it up the beach like this at an angle, and then it returns perpendicular to the beach due to gravity. And by this process, the water moves along the beach in a sort of sawtooth pattern, and as it does so, it carries with it sediment, and that causes sediment to move along the beach in this same sawtooth pattern, producing a net movement of sand parallel to the beach called longshore drift. This little animation going on here shows a little turtle being moved by waves which are coming in at this angle here, and if you just watch the thing play through, the little turtle is going to move from the right hand side of the frame to the left hand side of the frame as it follows a path like this, that sawtooth pattern movement of longshore drift. You can often see the direction of longshore drift by looking at the distribution of sand on a beach where they've erected perpendicular barriers to trap sand. We're going to talk about these later. These barriers here are called groins, and their purpose is to trap sand, and you can see that that's exactly what they're doing. So if the waves are coming in as indicated here, coming in to the beach at an angle, this will cause a longshore drift indicated by the blue arrow here to the south in this diagram, and that sand will then pile up and accumulate against these groins, and there'll be depletion of sand on the other side of the ground, so the groins. So you can see the direction of longshore drift by just looking at where sand has accumulated up against these groin barriers. Let's now turn to the question of how sediment moves perpendicular to the beach. One of the forces responsible for moving sand perpendicular to the beach is wind. And wind's primary role is to move sand that's exposed on the naked beach, the beach where there's no vegetation, and to move it back into the back part of the beach, which is typically covered by vegetation. You can sort of see these little green spots which represent some kind of grasses starting to grow. This accumulation of sand then in the back part of the beach, which is often vegetated, these are called the dunes, and dunes are very commonly present in the back of many beaches, most sandy beaches. And the movement of sand into the dunes is primarily carried out by wind. The other major process that moves sand perpendicular to the beach is caused by waves. Regardless of whether the waves are coming at the beach at an angle, which causes longshore drift, or perpendicular, these waves have the ability to move sand either towards the beach or away from the beach. The basic idea is that the movement of sand, the direction of movement, is determined by the size of the waves. Small waves generally move sand toward the beach and thus result in an accretion of the beach or growth of the beach. In contrast, large waves generally move sand away from the beach, moving sand away from not only the recreational beach, this part here, but may actually move sand from the dunes. That accumulation of sand, vegetated accumulation of sand in the back of the beach, may actually grab sand from the dunes and move it not only onto the recreational beach, but move it actually offshore. However, large storms are also capable of moving sand in the other direction. Occasionally, very large storms will overtop the dunes and by that process actually move sand from the front here of the beach all the way to the back. Areas that really weren't even part of the beach get covered up by the sand moved in this manner, and we call that overwash or washover. Because wave energy tends to be seasonal, the profile of the beach tends to be seasonal. For example, in Florida, summer waves tend to be small, resulting in accretion of the beach, while winter waves tend to be large, resulting in erosion of the beach. This little animation here is showing what happens during a typical winter phase, where the large waves are removing material from the beach and the dunes and moving it into the near shore area over here. What often happens during over here is what I'm talking about. What often happens is that sand is transported away from the beach and the dunes and accumulates as sandbars, which are located offshore. These accumulations, these undersea accumulations of sand called sandbars. The main point here to see as well is that the width of the beach here, indicated by the distance between those two vertical red arrows, decreases during the winter as sand is moved from the back part of the beach offshore. In the summer, this process is reversed. The small waves tend to move the sandbars back onto the beach, Wind blowing over the exposed beach tends to move sand to the back part of the beach where dunes can once again grow. And the beach, as indicated by the distance between these two vertical arrows, gets wider. So the beach gets wider in the summer and narrower in the winter. These effects can be seen in these two profiles of a seasonal beach, one in the summer and one in the winter. And hopefully you can see that the summer beach is wider and lacks offshore sandbars, while the winter beach is narrower and is characterized by offshore sandbars. You can also see on this little diagram that all this material here has been removed in the that's present in the summer has been removed from the summer beach and is actually residing out here under the sea. And we'll talk more about that later when we talk about the concept of a beach system.